Hello everyone, welcome to the course of Real-Time Embedded System. So today we will continue our chapter number 5, Program Design and Analysis. Today is our lecture number 26, and in today's lecture we will talk about program level performance analysis. So let's get started with the outline. So in today's topic we will talk about program level analysis. We will talk about optimization for execution time, energy and power, and we will talk about optimization for program size, and finally we will end this discussion at program validation and testing. So let's get started. So as we know that embedded system must perform function in real time, we often need to know how fast a program runs. The technique we use to analyze program execution time are also helpful in analyzing properties such as power consumption. In this section, we will study how to analyze programs to estimate their run times. We also examine how to optimize programs to improve their execution time. Of course, optimization relies on analysis. It is important to keep in mind the CPU performance is not judged in the same way as a program performance. So, CPU performance is not equal to program performance, as you can see in this slide. Certainly, CPU clock rate is very unreliable metric for program performance. But more importantly, the fact that CPU execute part of our program quickly doesn't mean that it will execute the entire program quickly or at the same rate. As you can see in this figure, the CPU pipeline, and cache act as a window. So these caches of CPU and pipeline acts as a window into our program. So this is a window for our program. In order to understand the total time of our program, we must look at execution path. So this is total execution path. So this is total execution time, which is general are far longer than pipeline and cache window. So our execution time is far longer than the cache and pipeline window. The pipeline and cache influence execution time, but execution time is a global property of program. So we must analyze the entire program. Let's move to next slide. So execution time of program could be precisely determined. This is in fact difficult to do. So complexities of program performance. Number one varies with input data, different length path. The execution time of a program often varies with input data values because those values select different execution path in the program. For example, loops may be executed at varying number of time. Different branches may execute blocks of varying complexity. So we will have different length paths. Number second is cache effect. The cache has a major effect on program performance, and once again, the cache behavior depends in part on data values input to program. So cache and input data also influence the execution time. Finally, instruction level performance variation, pipeline interlocks. Execution time may vary even at the instruction level. Floating point operations are most sensitive to data values, but normal integer execution pipeline can also introduce data dependent variation. In general, execution time of instruction in pipeline depend not only on the instruction but on the instruction around it in the pipeline. So pipeline interlocks mean that the instruction in the pipeline depend upon the instruction around it in the pipeline. So it depends upon the neighboring instruction as well. So the floating point operations are most sensitive, whereas normal integer execution pipeline can introduce data dependent variations. So how we can measure the program performance? Number one is that many microprocessor comes with simulators, so we can simulate our program with some specific input, and then we can measure its execution time, which makes CPU state visible. The other thing is that we can use timer, so measure on real CPU using timer. So we can use timer to check how long a program takes to execute. So it requires modifying the program to control the timer. So we need to modify our program so that the timer started at the start of the code and it gets stopped at the end of the code. And the timer is connected to microprocessor bus, can be used to measure performance of executing section of codes. The code to be measured would reset and reset the timer at its start and stop of the timer at the end of the execution. So our code must need to start and stop the timer. Finally, a logic analyzer can be connected to microprocessor bus to measure the start and stop times of the code. So we can use logic analyzer and connect it to the CPU bus. And it requires event visible on the pins. So pins basically means that buses. So this logic analyzer require events to be visible on the bus. So three different types of performance measures on program. Number one is average case execution. This is the typical execution time we would expect for typical data. Clearly the first challenge is defining typical inputs. So that's the typical execution time. Number second is worst case execution time. The longest time the program can spend on any input sequence is clearly important for systems that must meet deadlines. So a component in deadline satisfaction. Number third is best case execution time. This measure can be important in multi-rate real-time systems. So one is for typical execution time, one is deadline satisfaction, and one is for multi-rate real-time system. So this is how we can say that these are the program performance metrics: average case, worst case, and best case. So element of program performance. The key to evaluating execution time is breaking the performance into parts. So we have to break the performance into parts. Program execution time can be seen as execution time is equal to program path plus instruction timing. So once we add instruction timing and program path, we can find out the execution time. Solving these problems independently helps simplifying analysis. So the path is the sequence of instructions executed by program. The instruction timing is determined based on the sequence of instruction traced by program path, which takes into account data dependencies, pipeline behavior, and caching. Luckily, these two problems can be solved relatively independently. So in this slide, we will talk about data dependent paths in an if statement. So here's the code and here's the path. The conditional test and assignments are labeled. So these are tests T1, T2, T3, and these are assignment A1, A2, A3, and A4. So the conditional tests and assignments are labeled with each if statement. So we have labeled with each statement to make easier identifying the path. So what path should we take? We can list down all the paths with the help of truth table. The paths are controlled by variable in the if statement. So these are our variables A, B, C. So these paths are controlled by the variable. For any given combination of values of those variables, we can trace through the program to see which branch is taken at each if and which assignments are performed. For example, when A is equal to 1, B is equal to 0, and C is equal to 1. So we are talking about this particular case. A is 1, B is 0, and C is 1. Then test T1 is true. So because one of them is 1, so this test is true. and test 2 is true, because once this is fine, it comes here inside the nested if, and C is 1 in this, so test 1 and test 2 both are fine. So we can have assignment A1 because it is related to this particular if. We are not coming into the else, and then we are coming into Z, so assignment number 3. Okay, so because this if is true, we are not going to go into else. Okay, so only 2 assignment and 2 test. This means we first perform assignment 1, and then assignment 3. Okay, so we have performed assignment 1 and assignment 3. So this is with this if, we are not coming in else, so this A3. So these are 2 assignments. Notice that there are only 4 distinct cases: no assignment, assignment 4, assignment 2 and assignment 3, or assignment 1 and assignment 3. So these are different one, like no assignment, this is, we don't have any repetition for this one. Then assignment 2 and 3, here we have 2 and 3, here we have 2 and 3, here we have 1 and 3, we have 1 and 3. So 1, 2, 3, 1 and 3, and 1, 2, 3, 2 and 3, and finally we have assignment 4. So if you check all these paths, we have only 4 distinct cases. These correspond to possible paths to the nested if. So we can have only these 4 possible paths. Either we can have assignment 4, either we can have assignment 2 or 3, either we can have assignment 1 or 3, we can have no assignment. So these correspond to the possible path through the nested if. The table adds value by telling us which variable values exercise each of these paths. So in this slide we will list down the path through a fixed iteration for loop. Is seemingly simple. In the code below, as you can see here, this code, for I is equal to 0, f is equal to 0, I is less than n, I plus plus. F is equal to, so f is equal to f plus c of I into f of I. So our f will remain 0 all the time because we are not incrementing f. I is equal to 0, here is the CDF of this loop. I is equal to 0, f is equal to 0, then we are checking I is less than n has some fixed value. So if I is less than n, what we are doing? We are accessing the value of c and multiplying it with x, and then we are incrementing I, and then we are going again back to our conditional and checking the condition. If the condition is positive, we are coming back here again and again. So basically it is just like a is equal to a plus some continuous loop. So by examining the CFD for the code, we can more easily determine how many times various statements are executed. So if we look at this diagram, we can easily tell how many times this CDFT will execute. And if you remember, this is just like in code for FIR filter. Okay, so these are 2 coefficients multiplying, and then we are adding it with f and saving all the results in f. Now the CDF makes it clear that loop initiation block is executed first. So this is the loop initiation block executed, and this is executed only once. And the test is executed, this test is executed n plus 1 times. Because why we are executing is n plus 1 times? Because I is starting from 0. So we have to execute it n plus 1 times. Or we can say that at n plus 1 times, if we execute it, our condition will get fail. And the body and the loop is, so this condition will execute at n plus 1 times. However, this body which includes f is equal to f plus c of I into x of I, this will be executed n times, and this loop variable will be incremented n times. Okay. To measure the longest path, we must find the longest path through the optimized CFT. So this is the longest path, as you can see here. Since the compiler may change the structure of the control and data flow to optimize the program implementation, it is important to keep in mind that choosing the longest path through CDFG as measured by number of nodes or edges touched may not correspond to the longest execution time. So this could be the longest path, but this could not be the longest time-taking path. Since the execution time of a node in CDFT will vary greatly depending upon the instructions represented by that node, we must keep in mind that the longest path through CDFT depends on execution times of the node. So the longest path always depends upon the longest execution time of the node. In general, it is a good policy to choose several of what we estimate are the longest path through the program and measure the length of all of them in sufficient detail to be sure that we have in fact captured the longest path. So let's get moving. So this is the path initialization. This is the longest path. It includes loop test, loop body, loop variable update, and this is executed loop exit statement. So in this slide we'll talk about the instruction timing. Once we know the execution path of the program, we have to measure the execution time of the instruction executed along that path. The simplest estimate is to assume that every instruction takes the same number of clock cycles, which means we need to count the instruction and multiply it by the pre-instruction execution time to obtain the program total execution time. However, even ignoring cache effects, this technique is simplistic for these reasons. So the reasons are, not all instruction takes the same amount of time. We can have multi-cycle instruction which requires multiple cycles. Execution time of instructions are not independent. So one instruction time can depend on the other instruction time. So it includes pipeline interlocks and cache effects. And lastly, execution time may vary with operand values. So if we have integer, we have different time. If we have floating point operation, we will have different time. If we have multi-cycle integer operation, we will have different time. So these are the instruction timing. We can handle the first two problems more easily than the third problem. We can look up instruction execution time in a table. The table will be indexed by opcode and possibly by other parameter values such as register use. To handle interdependent execution time, we can add columns to the table to consider the effect of nearby instruction. Since these effects are generally limited by the size of CPU pipeline, we know that we need to consider relatively small window instruction to handle such effects. Thus far, we have not considered the effect of cache because the access time for main memory can be 10 to 100 milliseconds, 10 to 100 times larger than the cache time. Cache can have huge effect on instruction execution time by changing both the instruction and data access time. Cache performance inherently depends on the program execution path since the cache content depends on the history of access. So the measurement-driven performance analysis is the most direct way to estimate the execution time of a program by measuring it. Now, not so easy as it sounds, must actually have access to CPU, must know data inputs that give worst best case performance as we have discussed, must make state visible. Still an important method for performance analysis. So this is a method by which we can measure the performance of a program. It is not as easy as it sounds. This approach is appealing, but it does not have it does have some drawbacks. First, in order to cause the program to execute its worst case execution path, we have to provide the proper inputs to it. Determining the set of input that will guarantee the worst case execution path is infeasible. Furthermore, in order to measure the program performance on a particular type of CPU, we need the CPU or the simulator. Despite these drawbacks, measurement is the most commonly used way to determine the execution time of embedded software. Worst case execution time analysis algorithms have been used successfully in some areas, such as flight control software, but many system design projects determine the execution time of their program by measurement. So in this slide we will talk about feeding the program with inputs. Need to know the desired input values. We need to know the desired input values. May need to write software scaffolding to generate the input values. So we need to write a software to generate the input values. Software scaffolding may also need to examine output to generate feedback driven inputs. So we need to examine the outputs after giving the inputs so that we can generate the inputs. So this is called feedback driven inputs. So just like the way we talked in our previous slide that a way to analyze program is through measurement, another way to analyze the program for performance is through trace driven measurement. So a trace is usually a program to record the execution path of a program that has been measured during program execution. So it saves the information about the path it requires to modify the program. If we can measure a trace from running program, we can avoid the need of CDFG to determine the execution path. Traces are typically large since we usually need to look into the execution history, so widely used for cache analysis. Traces are in gigabyte size, however, because disks to hold the traces are inexpensive and workstation to analyze them are fast and cheap, traces are an appealing way to analyze program. We have to consider two problems: how to generate a trace and how to use it to determine program performance. As I've talked to you about the physical measurement, in physical measurement we can measure the time of the program execution with the help of timers, and in that case we have to modify our code so that timer can get started and then it gets end at the or gets stopped at the end of the program. And another way for physical measurement is logic analyzer can measure the behavior at pins or bus. Address bus can analyze to look for events. So we can look at the address bus for number of events. Code can be modified to make event visible. Particularly important for real-world input streams. So we can prefer this physical measurement program performance analysis for real-world input streams. So where we have data coming from the real world, we use timers and we use logic measurements for program analysis. So as I've told you that we can measure program performance in variety of ways. We just discussed that for real world input data we prefer timers and logic analyzer. However, we can also measure the program performance by using a simulator. So some microprocessor manufacturers supply simulator for their CPU. Some simulators are less accurate. Cycle accurate simulator provide accurate clock cycle timing. Simulator basically models CPU internals. Simulator writer must know how CPU works. So in this slide we will talk about what are the driving forces or what is the motivation behind the performance optimization. So as we know that most of the embedded system require that they need to finish the task or program to meet some deadlines. So we want the system to be faster, and faster does not mean that fast enough. So we need to keep on improving. Secondly, need to able to analyze the execution time. We need to analyze the execution time. So worst case, not typical. As I've told you, the longest time that program can spend on an input sequence. So this is important. Worst case, not typical. And lastly, we need techniques for reliably improving execution time. We need to know what are the techniques, what are the methods by which we can improve the timing of the execution of the code. So that was it for today.